So welcome to this introduction to 5G. I'm going to give an overview of 5G, some of its technology, some of its enablers, and some of the key concepts here. So you've probably heard a lot of the hype, and service providers are starting to roll out 5G across the world. Um, and 5G is the fifth generation of wireless technology, first starting from 1G in 1979 with NTT and car phones in 1983 with the analog mobile phone system in the US, mostly focusing on person-to-person communications, establishing basic voice wireless and phone calls. Moving on to 2G in 1993 with General Spatial Mobile Code Division Multiple Access, providing simple texting, simple email, personal communication systems. And then Universal Mobile Terrestrial Communication Services in 2001 with Docomo pioneering 3G, giving access to the web and people to machine communications. And then, of course, everybody's familiar with 4G because that's where we are now with high definition streaming, FaceTime, video chat, and smartphones. And then as we move into 5G, the Internet of Things, smart cities, autonomous cars, machine-to-machine communications, and remote robotics will be commonplace. So some of the big ideas in 5G are that we'll have media anywhere and enhance our current broadband experience, incorporating VR and AR, massive machine type communications allowing for the facilitating the Internet of Things, machine to machine communications, and supporting geographically spread devices. And then URLLC facilitating Industry 4.0 with remote device control, and things will be more smarter, connected, able to collaborate, greater access with higher speeds, and things will be much more interactive and more aware of their surroundings than they are currently. So probably the three biggest ideas in 5G are enhanced mobile broadband, URLLC, and massive machine type communications. So if you walk away with nothing else from this presentation, keep these three big ideas in mind. If you remember some of these three big, if you remember these three big ideas, I think I've done my job. So this will make you dangerous at a cocktail party. Enhanced mobile broadband is a spectrum extension, wireless capacity up to 1,000 times what we have today, FR1, FR2 centimeter and millimeter wave networks, and connecting everybody on the planet. URLLC enables what's called the tactile internet with ultra low latency, a sub-millisecond latency with perceived zero downtime, and then massive machine type communications, enabling massive connectivity, up to 1 million devices per square kilometer. And if you work out the math, that's one device per 0.92 square feet. Machine-to-machine communications, and of course, the Internet of Things. So to give you a sense of the speeds that 5G brings, 3G, the speeds at 384 kilobits per second in 2001 with latency of 150 milliseconds. 4G at 100 megabits per second in 2009 with latencies of 90 milliseconds, and 5G upwards of 10 gigabits per second with 1 millisecond latency. So to bring this down to earth, to give you an example of trying to download a 4.4 gig high definition movie would have taken 26 hours in 3G, 6 minutes in 4G, and 3.55 seconds in 5G. And what's important about the latency is 1G and 2G and 3G, the reason why there was so much focus on voice was because your ear, 150 milliseconds is what your ear can detect. So if, for example, I pause in my speaking, you can detect that, and those pauses in your ear can hear that. 90 milliseconds, 20 to 90 milliseconds is roughly what your eye can detect, and that's why there's a 60 hertz refresh rate on TVs, right? 1 millisecond, what's unique about that is the speed at which your touch can sense. So when you touch something, your sense of touch it happens on the order of 1 millisecond, very rapid. And that is why 5G gives rise to a tactile internet. So the concept of a tactile internet is where there's some kind of interface, a human-computer interface. There's and that can interact remotely with something that's tactilely teleoperated. So for in this example, a robot, watering your plant. When you're on vacation, you can control maybe a robot far away, or a first responder could control an emergency vehicle going into a fire. And the sensors on the robot's hands sends back information, which gives information back to the user in probably like a glove that you would wear. So haptic feedback back to the human computer interface. The Internet of Things. So we see here a chart of the number of connected devices that we have to the net. So the very first device was at Carnegie Mellon University in 1983. They connected a Coke machine to the internet. And we see here in 2003, let me turn my pointer here. So 2003, we have 500 million devices in 3G. And then as we rise into 4G, we have 5 billion devices, and then today we have 50 billion devices connected to the network. Okay, so again, the three big ideas. If you walk away with nothing from this presentation, these three key 5G ideas: enhanced mobile broadband, addressing system capacity, increasing the potential system capacity by 1,000-fold, 10 gigabits peak data rate, better spectrum efficiency, ERLC used for mission critical type applications where latency is super critical, super high reliability and high availability, and then massive machine type communications, affording extreme densities of 1 million devices per square kilometer. And of course, that allows for many machine-to-machine applications and IoT. So 5G has three basic bands that that the standards and devices, 5G base stations will operate in. And different countries will open up different parts of the spectrum, but generally speaking, they fall into three basic categories. So sub 3, so from below 3 gigahertz is the centimeter wave. From 3 to 6 gigahertz is the mid-band frequencies, sometimes called the C-band, and then the high band 5G is a millimeter wave. So these two are also called FR1, and the high bands are called FR2, or in the FR2 from the standards. Now, centimeter wave is going to be have less performance than the millimeter wave. So you'll have roughly similar to 4G performance at 100 megabits per second. The midband offers 2 gigabits per second downlink speeds, and then in the millimeter wave from 24 to 52 and on up. So the release 17 specifies even higher spectrum than this, will offer the very high 10 gigabits per second. So some of the things that 5G addresses that are pain points are things that couldn't be addressed in 4G, or things that are enhanced in 5G is, in energy and utilities, being able to integrate new technologies, handle large volumes of data, improved automation. Of course, Industry 4.0, which we'll talk about in a second, improved connectivity and real-time communications, machine-to-machine communications, a lot of new interesting applications in public safety to improve response times and improve coordination between teams, and healthcare for managing data and security and patient access. Public transportation, reducing congestion, concepts of things like platooning and vehicle-to-vehicle communications, and of course, the most personal things are media and entertainment, where you'll have better and improved capabilities to access social platforms and improve streaming and download, and improved latency. So some of the things that we anticipate that 5G will bring to service operators is increased network performance, 5G will require a lot more, especially if you roll out millimeter wave, it will require a lot more base stations, but that also brings with it better coverage and improved capacity, higher speed, lower latency, high peak data rates, scalability, massive device connectivity, embedded security and service awareness, better cost efficiency with reduced CapEx and OpEx, energy efficient network infrastructure, and of course, many new business potential, new business models, IoT, and many revenue capabilities, and just the huge amount of new use cases that are opened up by 5G. So to give you a little bit more of a sense also between the low band, the mid band, and the high band, so the low band has, typically base stations have, 10 to 20 mile reach. Now this has been around, this kind of reach has been around since 1G. So this is not really any different than we have today. So macro cells in 5G macro cells will still have that sort of reach, be applied in rural areas, but also have, similar to 4G performance, right? And wavelengths of 30 centimeters. When we come to the midband, that it would be deployed probably in an urban setting with a reach of a mile or 1.6 kilometers, and have again in the range of 1 to 6 gigahertz with wavelengths of 4 centimeters. And then the above 6 gigahertz has, just due to the physics of millimeter wave propagation, it doesn't propagate that far, 150 meters or 490 feet, with wavelengths of, in the on the order of millimeters, 6 to 8 millimeters. Okay, so some of the applications, which I think there are literally going to be, hundreds and hundreds of new interesting applications that 5G will bring. So we can sort of think about these in human to human, human to machine, and machine to machine interactions. So, and the three big ideas with enhanced mobile broadband, massive machine type communications, and ultra reliable low latency communications. So with human to human, the concept of virtual reality and augmented reality, where you can simulate something, or you can enhance your current reality, meaning that you can, for example, overlay, like your phone could overlay what it sees with navigational pointers, or tracking inventory and visualization of things before you move them, for example. Of course, we're familiar with video calling and virtual meetings like we're having now. Wearables and other devices that talk to other devices. So for example, like the Ring smart doorbell, it can talk to your phone or your watch. And of course, social networking we're familiar with. And then ultra reliable low latency communications, you can imagine in public safety, where first responders, a firefighter might be able to control or send in a robot or something, or a drone into a fire without putting themselves in danger. Human to machine communications with enhanced mobile broadband allows for fixed wireless and ultra high definition video, and massive machine type communications enables smart cities and smart homes with improved healthcare monitoring. And some of these ultra reliable low latency applications are foreign to us now, but will be commonplace 10 years from now. So the ability of, say, remote procedures, remote medical procedures, remote triaging, remote first responders, performing simple medical examinations from halfway around the world, or when there's a disaster and there aren't enough emergency responders, doctors, and policemen and firemen, but those in other countries or other states or other areas can help out. Vehicle to pedestrian, so you being aware of cars being aware of people, so they don't crash into each other. And of course, vehicle to vehicle communications, the concept of something called platooning, which is where basically vehicles talk to each other and can synchronize, so they're traveling in lockstep and reducing the chance of accidents and fatalities. So you can imagine that that's also a lot more energy efficient. Vehicles talking to the infrastructure, we kind of already do this today with smart traffic lights, or traffic lights that have sensors that can detect when they should go green or a car is waiting, but we'll have a lot more things like that we don't have today. So for example, parking spots, an empty parking spot can tell nearby cars, I'm free, there's a place to park for you to park, as an example. Or smart roads that can detect when there's hazards in the road. So if you've ever used the Waze application, it's similar to that, except right now Waze is very manual. People have to punch in, I see a pothole in the road, or I see an obstacle on the road. Industrial automation, so we'll talk about Industry 4.0 in a bit. Enhanced mobile broadband, allowing for mobile cloud computing, fog computing, edge computing applications, and video monitoring will be enabled by, or just some of the ideas in 5G. So this is also a chart of some of the examples of some things that are enabled by 5G. So we see where we come to 1 second latency to a tenth to 10 millisecond to 1 millisecond, and then the bandwidth, things that use bandwidth, so less than a megabit per second up to more than a gigabits per second. So the things in the white area here are things that are already supported in 4G, disaster alerts, automotive calls, device remote monitoring, monitoring sensor networks, real-time gaming, first responder connectivity, personal clouds, video streaming. So in the dotted line here are machine-to-machine type applications where we have devices talking to other devices, bidirectional remote controlling. But of course, these are using 10 millisecond latencies in 4G. There is something called narrowband IoT and enhanced machine type communications in 4G, available in 4G, which are dedicated, you might have heard of Cat-M, category M, in 4G. So those are specifications that are in 4G that help address the needs of device-to-device communication, but there'll be more of that in 3GPP release 16 and 17 that or are already in 16 and that came out last December, and coming up in 2021, release 17 of the 3GPP specifications, which we'll talk about more in a bit. So some things here in the gray you see are things that are really enabled by 5G. So like watching James Bond drive a car autonomously, I mean, that would be possible in 5G, which would be completely impossible in 4G. But of course, you might not actually ever drive your car from your cell phone, but you can imagine a firefighter or somebody going to a disaster area, or there's been an accident or there's flood or tornado or whatever, to drive a robot to help and pull out people or to save people, that kind of thing, right? Augmented reality, again, is where a device can overlay your current location with extra information. So for example, suppose you're walking down the street in a city downtown, and augmented reality can tell you, if as you're walking, it can tell you what stores, it overlays your current reality with extra information. So it tells you what kind of stores are there, or maybe they have some sale or something. The tactile internet, so we talked about the sub-millisecond latency, so opening up many applications for a tactile internet where you could, you have applications related to touch instead of just sight and hearing. And then of course, virtual reality, being able to emulate virtual environments. So you could take virtual tours of museums, or and suppose you're traveling in Florence, you could take a virtual tour of the Uffizi when you're nearby instead of actually going there. And then of course, multi-person video calls and a wireless cloud-based office are some of the things that are on the edge of between 4G and 5G. They're things that are kind of available now, but are greatly enhanced with 5G. So I'll talk about some of the applications in 5G, and you can start thinking about, that gets you to start thinking about some of the applications in 5G. So many of these things are potentially capable in 4G as well, but again, greatly enhanced by 5G, 5G's capabilities. So you can imagine smart door locks, enhanced security systems, a smart air conditioner, lighting control systems, energy management, appliance control, smart thermostats, and smart bathroom appliances and garage door openers. So Nest, if you've heard of Nest, is a, a company that was acquired by Google. Originally, the Nest company created smart thermostats. So a thermostat that can be aware of the people when they're home or not and adjust temperatures accordingly. And you can imagine also where you might be able to have zones eventually in a home. It can tell you, intelligently tell you when it expects to reach a particular temperature. So if you dial it up to say 70, 75 or something, today's thermostat you just do it and it does it whenever it happens. Whereas the Nest uses colors and feedback to give a person a sense of when it's going to achieve that temperature. Smart doorbells. So we have the Ring doorbell, if you're familiar with that, is basically like a smart IoT doorbell, which basically can talk to smartphones where you can see who's there at your door and answer even when you're away. Okay, wearables, of course, the uh, smart clothing is something that we don't have much of now. Of course, people are pretty familiar with smartwatches, but they'll be even more enhanced with, you can imagine maybe a holographic display or an overlay display where you're interacting with a larger screen or projective screen. Smart clothing, um, when IoT devices become very commonplace, cheap and small, you can imagine things like a Fitbit that can give you a feedback or give you information about how you're doing, monitor your health and things like that. Um, that can't be done today. So I attended an interesting talk from a professor from MIT. They gave me they cited an interesting example where basically because of millimeter wave communications, 5G base stations can also tell where somebody is in a building or a home, and by they can also tell basically if they're standing or sitting or prone. So you can imagine those those uh, um, those health uh, those health tags where it basically says I've help I've fallen down. You can imagine your parents where they've fallen down, they can't get up. 5G would enable them to wear something like a smart watch or smart band or smart clothing where they can tell if somebody's suddenly fallen down, right? So it's expected to be a pretty large market, 43 billion by 2024. Smart cities, again, estimated to be a pretty large market, 135 billion. And you can imagine lots of different potential applications in a smart city, ranging from emergency services, power management, and public safety, to smart parking we've talked about, augmented reality, being able to tell as you walk through a city, the city can tell you information about itself, where things are, or historical landmark information on historical landmarks. Um, Connected car services where vehicles can essentially talk to each other to let them know of their presence, to avoid accidents and collisions, or just even to have more efficient travel. So you can imagine a city of the far future wouldn't need traffic lights at all. If I know exactly when cars are going to arrive at an intersection and at what speed, you can just simply completely coordinate cars passing by each other. So when they come to an intersection, there's no need for a stoplight, right? As an example. And then smart utility, sanitation management, and so forth. So we see some ideas of smart intersections, solar panels, smart streetlights, and smart waste management, emergency departments, bus stops. Allowing people to see exactly on live wait times and parking apps. So there is a whole, if you do a little bit of searching like I have, you'll find a lot of information on IoT in the automotive industry already. Advanced telematics and roadside assistance, entertainment, audio, video, collision avoidance type things, diagnostics. So if you're aware of something called OBD, onboard diagnostics, OBD2, which is available to mechanics. So when your mechanic looks at your car, he can connect to its computer and tell you and see all sorts of stuff about what's going on. But imagine that being available just say on your cell phone, things like that. Low speed networks, security, enhanced security, like with locks and auto locks and security breaches in your car. Wireless networks, something called ADAS, Advanced Driver Assistance Systems, and DRSC, Dedicated Short Range Communications for vehicle-to-vehicle communications. I talked about the concept of platooning and software updates. So Tesla has pioneered some of this, being able to update your software in your car. Okay, so 5G, some ideas of 5G applications in the healthcare industry: context-aware patient privacy, faster and less manual check-in, context-aware data and analytics, location-aware and asset tracking. So like my cousin is an anesthesiologist, and he tells me, there's like more than 1,000 different surgical devices, and being able to keep track, or trying to keep track of all those things, I can imagine isn't an easy thing to do. Context-aware measuring and recording, location-aware awareness to a nearest doctor, context-aware post-visit care. So I have 3 friends that have had recent medical incidents. For example, one of my friends broke his foot, and so he has a screw in his heel now, and right now that's of course a dumb device, but in the future that might be a smarter device. Another friend of mine had a heart incident, not a heart attack, but a heart incident. Now he has a sort of a defibrillator thing implanted in him, and but now it requires a very manual, sort of a manual post-care thing where he's got to attach that to a computer to and then interact with the doctor in a very manual way. And you can imagine that kind of thing, of course, would be much more intelligent in the future. Smart access control for security and navigating, for allowing, today, when I last went to get a checkup, every time I go to this hospital, it's hard to find my way there. When I have to try to find departments and places. So Industry 4.0, you can imagine that lots of things will be facilitated, and lots of new interesting applications related to industry and manufacturing. Industry 1.0 was essentially the Industrial Revolution with the Newcomen and Watt steam engine, Jacquard loom. Industry 2.0 with, like in the 1864, 1868, the first assembly lines to make rifles in the American Civil War, up to 1905 with the Ford Model T, assembly, one of the most famous assembly lines, and mass production and the concepts of an assembly line. And then Industry 3.0 integrating, of course, advanced computers and electronics. And then 4.0, cyber physical systems, IoT, and advanced networks will be the basis of Industry 4.0. Enhanced safety monitoring for of course, trying to avoid accidents of people working in industry, assembly line management, just-in-time management, so having inventory or parts arrive just in time as you need it saves on time and increases efficiency. ERP, enterprise resource planning, to allow the management and coordination of resources. Cyber physical systems, so augmenting people with and integrating them into the factory. Machine-to-machine communications, of course, we'll talk about that in a second too. RFID controls, being able to have things ID'd as they come in to track parts and things in the factory. Factory security, so enhanced factory security when things are aware of each other. Of course, robotics are already used a lot in manufacturing. If you've ever seen documentaries like How It's Made, come to realize just how much of the world already uses robotics for manufacturing. It's really amazing. So when you watch any of those, if you've never seen it, just Google or do a search on How It's Made and watch a couple of those documentaries. They're only like 30 minutes long. You'll see that robotics are already, and automated things, maybe not necessarily like what we might think of as like a Jetsons robot, but like assembly line machines that are dedicated to do a particular task, to move this piece to there, or to weld something here or add a rivet there, are already a very integral part of Industry 3.0. PLC, MES, MOM, and SCADA. These 3 form a triad of control, planning, and supervision, where basically you can control particular devices today you can plan to and execute on a particular manufacturing layout, and then supervise and watch and control everything as the factory gets underway. So you can also imagine Industry 4.0, you can dynamically reconfigure factory assembly lines easily based on needs as parts of a factory could become a lot more interchangeable and dynamic. Today, when you set up a manufacturing line, it's very static, I would say. So again, if you watch some of those documentaries, they're wonderful documentaries, you'll see that there are lots of dedicated devices and belts and things that do things in a specific way. And Industry 4.0 will be much more dynamic, I think. Okay, so 5G is rolled out. I'll talk a little bit about the fundamentals here. So 5G has rolled out in 5 phases. The first, fixed wireless access, and then last year with some smartphones and mostly focused on enterprise rollout. And we're just starting to see enhanced mobile broadband, so better performance and higher average speeds, better spectral efficiency, higher capacity. A lot of service providers around the world have invested, $1.7 trillion to try to roll out 5G, which requires a tremendous new amount of technology and base stations to roll it out. And there's a focus on mostly on centimeter wave because that offers greater coverage. So as we're just starting to roll stuff out, of course, you want to focus on centimeter wave to get that greater coverage, and then eventually, as you start rolling out more millimeter wave stuff, you'll be able to do interesting massive machine type communications and ultra low latency, high reliability type things. So the MMTC and URLLC are a little bit more dependent on having a much more millimeter wave FR2 type deployments than here. There's a lot of focus on FR1 just to get a network rolled out. So some 5G performance requirements, the peak data rates of 20 gigabits per second downlink, uplink speeds, a high downlink of 100 megabits per second, ultra reliable low latency, of course, in the user plane 1 to 4 milliseconds, and in the control plane 20 milliseconds, maximum speed for handoff and QoS quality of service requirements at 300 miles per hour or 500 kmh, a connection density of 1 million devices per square kilometer, and that's roughly 1 device per square foot. Energy efficient, so equivalent to at least a 4G, and spectrum efficiency, a throughput per unit wireless bandwidth and per network cell of 3 to 4 times that of 4G, area traffic capacities of 10 megabits per second per square meter, transmission carrier bandwidth of 100 megahertz, and 5 nines reliability, so 1 times 10 to the negative fifth successive probability of transmitting a layer 2 PDU. Okay, so this is just a typical architecture you might see in between 4G and 5G. When in the standards, you'll see actually that at first 4G and 3G will be, of course, coexist together, and 5G will probably be used as sort of an overlay to 4G, and 5G will take some of the more dedicated 5G type applications and shunt other things off to 4G. And as 5G is just starting to roll out, 4G may take the bulk of a lot of the communications. But we see here, like a macro has a long reach, again, up to 20 miles, whereas a 5G millimeter wave type cell only has 150 meter reach, 490 feet. So you'll see different types and deployments based on geography, as well as type of rural or urban setting. So this is a view of a sort of more conceptual view of a 5G network where you have a radio unit, a distributor unit, and a centralized unit, and this forms a 5G base station where you have the modulation and demodulation in the radio. You have the modem functionality in the CU and the DU that does that takes the processing of the of the signal, of the RF signal, gets transformed into a digital signal. And eCPRI, Enhanced Common Public Radio Interface, which is an optical interface between the DU and RU, which is standardized to be able to send specific types of messages. And then, of course, front haul and back haul to send that into the core network. The user plane function manages, and session management function manage and track where a person is. The unified data management function and authentication servers and access management functions provide a newer architecture for security and authentication of a user, and then of course ONAP we're all familiar with to manage it all. So some of the enablers are new spectrum. So we see in release 15, 52.6 gigahertz and 39 gigahertz, release 16 frequencies greater than 52, and which isn't, I think, realized so much, but and then more emphasis on that in release 17. Advanced beamforming techniques, multi-connectivity that I just mentioned, standalone and non-standalone, option 3, 4, and 7. Of course, network slicing for dedicated type of traffic. Service software-defined networking, network function virtualization, edge computing, fog computing, and mobile edge computing. So software-defined networking is an approach basically to cloud management that facilitates network management and enables programmatic efficiency in a network. Network function virtualization to basically take services that are traditionally run on dedicated hardware and making those virtual. Fog computing is essentially bringing the computational power closer to the end user. So end devices basically have less distance to communicate to the computing engine, so that it's latencies are reduced. Beamforming was actually a concept from many decades ago, actually from the military, starting with phased array radars in like the I want to say 50s or 60s, where basically you can take radio signals and adjust their phase and amplitude such that they arrive at a particular point at the same time. And phased array radars have inspired many other technologies. For example, in ultrasound technologies, the transducer, the ultrasound head, uses that exact same technology to be able to zone in on, say, the flow of a heart valve, and 3D ultrasound that can take arrays of transducing elements and adjust them to such that the ultrasound waves arrive at the same point. And then of course we see that same concept, that same idea being used in wireless technologies as well. Beamforming has been around again for decades in wireless industry as well, but now we see more advanced arrays of those in 4G and 5G, where basically instead of just random radio waves, you can focus the energy in a more methodical manner. So those 12 stack dipoles that you used to see in 2G and 3G are now much more advanced arrays of beamforming arrays. So spectrum allocation, again, this will vary by country a lot, but but we see new spectrum being opened up for dedicated to 5G. Multi-connectivity, so the 3GPP standards define different kinds of, and they call them different options, basically option 1, 2, 3, 4, 5, 6, 7, so where basically we see different combinations of a 5G cell and a 4G cell that are working together essentially to provide service. So in the USA, we see some of the spectrum here where there's licensed and unlicensed spectrum, and there are licenses will be opened up to service providers and access to service providers and how they can be used. So in 4G, we have actually, I mentioned NB-IoT before in category M. So these are things that are actually will be greatly improved and extended in 5G, but the foundations of this are laid in 4G. So the narrowband Internet of Things is basically an LPWAN, low power wide area network, which is focused on trying to address machine-to-machine communications, and so is Category M, where basically we have lower speeds and basically if you think of like your cell phone today, you have to constantly charge it, right? So you don't want devices that are trying to connect to the internet to constantly recharge. Maybe they're just running on batteries, and you want, actually the rule of thumb is you want that thing to last 10 years on 2 AA batteries. So you don't want it to constantly have it communicate to the network, but only when it needs to and at much lower data rates, and that's what Category M is set up for. So I also mentioned EMTC, enhanced machine type communications, in, again, a 4G, starting in 4G with early releases as early as release 13 in June 2016 with LTE Advanced Pro. And we'll see more advancements of it. There have been more and more advancements of it in the standards. And here you see where basically we have the LTE Advanced, where you have a megabit per second up to a megabit per second, LTE-M with tens of kilobits per second, and narrowband IoT up to tens of kilobits per second. And some typical use cases of this are mobiles and video security, to wearables that can talk to a network, object tracking, utility metering, and environment monitoring. So these are all, you'll recognize these as some basic IoT type things as well. And 5G extends these capabilities of these concepts from 4G. And slicing, of course, the concept of slicing is pretty integral to 5G. A lot of people talk about it as well. And the idea is basically you can set up your network for different slices. So you can set up your RAN and core and transport networks so that they are catered to the needs of utilities or devices, or devices talking to each other, or focused on the needs of enhanced mobile broadband, or to achieve ultra reliable low latency. Or you can imagine a public safety slice that has needs or has priorities over maybe other slices as for emergency uses and first responders. So some key ideas that each slice is differentiated and associated with specific data flows, with differentiated quality of service and priority between flows, and dedicated network functions, privacy and segmentation between flows. And some of the slicing requirements are that there's adjustments that where you can tweak them through and throughput and latency, reliability, mobility, and security. And ultimately, this results in uh, um, sort of tailored graphical coverage, cost profiles, and exposure analytics and content enrichment. So mobile edge computing. Again, the concept is you have a bunch of devices, whether they're IoT devices or phones or individual monitors and things that are connected to servers in the cloud that are that are located closer to the end network, and those communicate to data centers, more centralized data centers, as they send information over longer distances. So some of the key ideas behind here are that the edge is local, meaning that it can run isolated from the rest of the network while having access to local resources. And this is important for machine-to-machine type communications. For example, when you're dealing with security or safety systems. Proximity, so being close to the source of the information, edge computing is useful to capture information for analytics and big data because you're closer to the actual location where that data is being captured, and the sensors are on site. Lower latency, so edge services, of course, are closer to the end devices, and that will considerably reduces its latency. So this allows the system to react faster, to improve the end user experience, or to minimize congestion in other parts of the network. And of course, the devices that are on the edge, of course, would be much more aware of the actual end device. So a network edge that's part of a wireless network can leverage low-level signaling information and information and provide services that are related to location, so location-based services and analytics that are location-based. And then network context information, so real-time network information such as radio conditions, network statistics, and applications that use that kind of information um, allow the network to be smarter and those devices trying to use the edge to be more intelligent. So we'll talk a little bit about the standards that are driving all of this. Here's a 3GPP standards map. It's from the S5197-548 document. And it gives you a sense of, if you look in the 3GPP standards, the OEM specifications are 28 or 32 series. There's 160 28 series documents, 460 32 series documents. So, there's like 500 3GPP documents, and each of which are 20 to 100 pages. So you can do the math. There's lots and lots of 3GPP specifications. So it can be quite a maze to figure out what does what and what's specified where and how they're all connected. So this is a pretty good reference to as a starting point for some of those standards. So the basic 5G management concept is in 28.530, the SBA service-based architecture is in 28.533, configuration management in 531, FM fault supervision in 545, performance assurance in 550, energy spectrum efficiency in 310, the 5G network resource model in 540 and 541, based upon 620, 621, 2, and 3 for the generic network resource model, the unified information model, and 532 for generic operations, measurements, and for performance measurements and key performance indicators in 552 and 544, generic services in 532, self-optimized networks in 313, closed loop and closed loop SLS in 535, and call tracing in 421 and 422, and intent-driven networks in 321, 312. Okay, so some of the we'll walk through some of the ideas in some of these standards. So release 15 and 16 talk about some of these different kinds of options that I mentioned before, talking about how a 5G base station and 4G base station could operate together, and there's different options that are described. Some of the timeline milestones we'll see in release 16, came out in December, or was targeted for December 2019, and release 17 in 2021. So release 16 talks about vehicle to everything type V2X, communications, industry 4.0, industry IoT, ultra reliable, low latency communication enhancements, 5G unlicensed spectrum operation, interference mitigation, SON and big data, MIMO enhancements, massive input, massive output enhancements, location and positioning enhancements, 5G power consumption, dual connectivity, device capability exchanges. And then we're coming on the verge of here, 27, the release 17, that's coming out in that's being specified in 2021, and we'll see them, we expect to see them, I think, being completed roughly in 2021 as well. And some of the release 17 will bring enhancements to 5G IoT. So I mentioned the narrowband IoT and enhanced MTC. So we'll see 5G versions of those with enabling smart cities and industrial IoT, low-end wearables. So these are lower bandwidth things and applications, low complexity, low power, and delay tolerant, that are aimed at device-to-device communications. 5G NR Lite for lower complexity devices with half duplex and improved control channel design. And then, of course, the higher performance stuff for eMBB, so high-end smartphones, streaming a video, or ultra reliable low latency communications that require very low latency, like controlling devices remotely. Release 17 will see centimeter level accuracy, meeting accuracies down to 0.3 meters, lower position latency, reducing latency from what it was, and then much higher capacity scaling to millions of simultaneous devices. We also see that 3GPP release 17 will have improvements in MIMO for better mobility, using the spectrum that I talked about before, enhanced duplex and spatial multiplexing, DSS enhancements, enhanced coverage for sub-7 gigahertz and millimeter wave. And there's even talks, of course, of, probably 10 years-ish from now, we'll see 6G, which will have even higher frequencies than we do today. So supporting bands and release 17 up to 71 gigahertz, multicast for content delivery, further power savings for idle, connected, and small data, further enhanced mobility for mixed topologies, and basically enhanced foundation for coverage, capacity, latency, power savings, mobility, enhanced deployments, new spectrum, and new services. So I talked a little bit about augmented reality. So there's also this new concept called XR, which is extended reality. So the augmented reality, again, you can imagine say, before you move furniture in your home, you can move your phone around and it can show you a picture of what the couch might look like on that corner, or you're walking up to a storefront that's closed, say a shoe store that's closed, and you wave your phone over it and it can tell you those prices of things without you having to be in the store or where there's a sale. Extended reality uses more of that with more simultaneous users, reduced latency, optimized power consumption, more seamless mobility, increased coverage, higher reliability, traffic awareness and system enhancements, and built on an edge processing framework. So of course, as we go into release 17, I think we'll hear more about this XR, extended reality concept. Okay, so that was my last slide, and I'll take any questions that anybody might have. I know there's a lot to absorb in an hour, but those are some of the, I think, the highlights of 5G and what it will bring. Any questions from anybody?
Yes, Ben, Kamal.
Yeah, hi.
Good morning, everyone. Yeah, really a very good presentation. You gave us a kind of a tour of all 5G evolution and applications.
Yeah,
this is really good. Yeah, my question is, I was thinking, I had this thought long time, but I just want to discuss it here. Mm-hmm. How we can evolve ONAP, which is our open network automation platform, mm-hmm. to cover the IoT technology or the MIoT.
Oh, that's a really good question. Yeah, mm-hmm.
I see that because what I want, I did some work on some projects in narrowband IoT. Mm-hmm. Here in the US, and mm-hmm. The challenge is that I see some manual tasks, some manual task where, for instance, I have to go to my portal and onboard my device, mm-hmm. and then so I have to do all the steps, the onboarding process. So for me, I was just thinking if I'm right, that I want something like what we did, not similar, but like the plug and play. I mean, the device. Mm-hmm. You take a device, when you power on the device, it bootstrap, and then it communicates with the IoT platform, and the IoT platform will onboard it will onboard it in. We'll do the device onboarding and then the device configuration. Like if you take the narrowband IoT, I know I'm familiar with the OMA standards, the Open Mobile Alliance. They stated all these lightweight M2M protocol for device communication. So yeah, my question is that can we do something like this where we evolve ONAP to cover the IoT devices? So today we are dealing only with the telco devices, 5G core radio.
Right.
So how can we
So I have a whole nother talk on IoT actually, so I think IoT is interesting because just of the sheer number of devices that are presented to the network. And we're really just at the beginning of this now. If the 50 billion is just scratching the surface of what we expect. So you know, when we hit into many hundreds of billions, or even a trillion devices, I think what it really boils down to is, if you ask how would we manage, what kind of network is needed to support that, I think the answer is that you'll see a lot more millimeter wave deployments. So in order to achieve that kind of density, not just the speeds, but the density of communications will require, I think, in my mind, more mid-band and more C-band and more high-band type deployments. And what that ultimately means is, and if you do the math, just the simple math of, if, for example, you just take the simple pi r squared radius, you'll see that between this, there's about a 5 to 10-fold amount of cells that you need to cover the same area, or the same 1 mile area, not 20 miles, but the same 1 mile area. So pi r squared, you take a mile and versus 500 feet. And what that ultimately means is, with that many more cells, you need that many more base stations, right? So you need that many more 5G base stations. And I think where ONAP gets involved is, we don't necessarily manage, even today, we're not really managing the radio units, and the cells are tracked, actually, will be tracked in the configuration precision service, the CPS, and the many more cells that are in that network, I think, will and the applications northbound of ONAP, I think, will be interesting. So really, it boils down to, what does ONAP manage, and what does ONAP need to be aware of, and what kind of analytics are dedicated towards IT. I think those three questions will affect the evolution of ONAP as it tries to manage IoT, right? So so I think we'll see, first of all, we'll see many more, I think potentially many more base stations, which means that we'll probably have greater sort of edge deployments of ONAP in order to handle that capacity and real-time types of operations that we want to do. When you have a lot more data being sent and moving around in that network, allowing for things for analytic opportunities. We'll see ORAN is already specifying a lot more real-time data collection and things like that. So I think that'll be interesting as well. So I think there will be, we're just, I think, at the start of some of the 5G IoT stuff and applications. Real-time ad hoc networks, where basically devices set up their own network together. There's 12 basic protocols that are used with IoT, and 5G and 4G are just one of those 12. So we see lots of different types of dedicated types of protocols for for IoT as well. So maybe we can talk about that in a future realization call, because I have a presentation on that as well, and we can talk about IoT some more. Okay, great question. Thank you. We are at time, so thank you everybody for attending. I hope you found this useful, and I'll upload the slides and recording after the call. Great. Thank you very much and have a great day. All right, bye.
Thank you. Bye.